Thanks. I'm Tom Mortal. I'm a postdoc here at Santa Cruz. And today I will be talking about observations of satellites in groups. And the reason I'm going to focus on groups is very simple. Most galaxies are, in fact, in groups. And a lot of the processes that kind of drive their evolution actually take place when they are in groups. And so at low redshift, at redshift 0, it's essentially you can do it in a fairly straightforward way using redshift surveys. And there's plenty of them. There's SDSS, of course, but of course Gamma and Z-Cosmos and others. And so you can make group catalogs or use statistical methods to kind of clustering and weak cleansing to kind of look at individual, either individual halos or a population of halos in general. But of course, if you want to study this, the evolution of galaxies in groups, then you have to go to high redshift, in which case even spectroscopic redshifts become insufficiently accurate. And so what you have to do is you have to go and rely on photometric surveys, which means that you have to do everything in a statistical way. And so the benefit of photometric redshifts is that, of course, you can go to really high redshift compared to spectroscopic surveys. And when I say statistical analysis, I mean the simplest thing that you can think of. And in this example, what I'm doing is just identifying a central galaxy or a primary galaxy, and then just counting galaxies around it in radial bands within a mass ratio of 1 to 10 and some redshift slice. And this is essentially a two-point correlation function. And of course, you have to account for the contamination by background and foreground sources. So you do the same thing. You repeat the same thing in randomly positioned apertures or random positions along the same field. And so what you're getting is two things. First of all, you get the radial distribution of galaxies around your centrals. And then you get the additional curve, which comes from the random apertures. And so if you now subtract one from another, you're left with just the satellite galaxies, or galaxies that are physically associated with your centrals. And of course, so I'm going to show you what it looks like. But before I do that, again, I want to study the evolution. So I have to match my samples over a fair range of redshift. And I have to do it in some way. And there are multiple ways to do that. The way I'm using is a method, a technique that's been used fairly extensively recently in the last few years. And it's based on a fixed number density selection. So what you're doing is you get the cumulative number density curves at a given redshift. And you repeat that for multiple redshifts. And then from there, you select a fixed cumulative number density. In this case, it's a few times 10 to the minus 5. And what you get from that is the growth of mass in redshift. So you allow your sample to grow in mass, to evolve in mass. And so I'm going to do the same thing using samples from SDSS and the new firm medium band survey, which is a photometric redshift again. Photometric survey. And I'm going to look at the distribution of satellite galaxies around my centrals. And this is what I'm getting. So this is just the projected average density of satellite galaxies around my centrals, all the way from 10 kiloparsecs to a few megaparsecs, and over the redshift range of 0 to 1.6. And the most interesting thing that you can see here immediately is that there's essentially no evolution. Essentially, all the curves lie on top of one another. And a naive interpretation would be, OK, this is a static model, static halo model. I mean, there are no mergers. Nothing's going on with these satellites. But of course, we know that there are mergers. We know that the centrals, we actually select them to grow in mass. We know that they grow in mass. We know that mergers are important inside these halos. So that kind of forces us to have this remarkable balance between mergers inside the halo and accretion of additional galaxies into the halo. And of course, this is not necessarily trivial, because the processes that govern in-halo mergers are completely different from the processes that govern accretion into the halo. And an additional nice thing here is that you might notice that the gray curve which is the prediction from the Gu et al. Semi-analytic models, actually lies on top of our observations. And the nice thing about this is that we can then go and see what happens to satellite galaxies in the SAM. And this is a little busy, so I'll kind of walk through it slowly. There's on the left y-axis, there's the fraction of galaxies, of satellite galaxies that merge with the central by redshift 0 as a function of distance, physical separation, at that given redshift. So for example, at redshift 1, if you look at galaxies that are more than a megaparsec away from the central, the probability of merging is actually very low. But as you go closer in, and galaxies within the virial radius, which is a few hundred kiloparsecs at this point, actually a lot of these galaxies are going to merge with the central. So most of these galaxies are going to merge with the central. So again, there's mergers do occur in these SAMs, and we know that. On the other hand, if you look at the inflow velocity of these, again, as a function of redshift and separation, you see that things that are far from the galaxy, from the central, actually fall in on essentially radial orbits or nearly radial orbits, and kind of don't spend a lot of time in the halo itself, unless they're very close to the central, and then there's some probability that they're going to merge, and they're on different orbits. So what does that mean? This actually brings up two kind of important questions. First of all, so we see that so these galaxies actually either merge with if they're inside the halo, they merge with the satellite, or they spend very little time in the halo. So what is the potential for growth? We know we measure the stellar mass growth. We know how much these centrals grow by. How much of it comes from these satellites? How much of it comes from mergers within the halo? So that's one thing. The second question is, OK, so if they really don't spend all that much time in the halo, what is the influence of the halo itself on its satellite galaxies? And can we measure it? And so to answer the first question, I can do that very quickly using the radial distribution curves that I showed you just before. And now this is the integrated number of, so I'm just integrating over those curves in radius. And this is the total number of enclosed satellites as a function of integration radius. And the first thing that you can do is kind of play a kind of pair count statistic game and see, OK, so if I go to 30 kiloparsecs, which is what often is done with pair count measurements, what fraction of these centrals have a massive satellite within a mass ratio of 1 to 10 within those 30 kiloparsec? And you see that it's 20%, which is completely consistent with pair fraction estimates. But of course, this is a generalized measurement, and you can do this for any radius that you want. So if you now go to the virial radius, which is again a few hundred kiloparsec, you see that there are between 2 and 3 satellites for a given halo. But the interesting part is that in terms of mass, there's a lot of growth potential, because in those 2 to 3 satellites, there's just as much stellar mass as in the central itself. So the central could double in mass just by merging with those 2 to 3 satellites. Thank you. OK, so the potential for growth is actually significant. OK, so to answer the second question, what I'm going to do now is actually go to so look at again groups in a large redshift range, and I'm going to utilize data from 3 catalogs, or actually 4 surveys. So at redshift 0, SDSS, NYU Valley-added catalogs, Ultra Vista, which is an infrared ESO survey, which recently had the first data release and public catalogs, and then Candles and 3D HST. And the catalogs come from the 3D HST group. These are just photometric catalogs based on Candles data in addition to the 3D HST data. And so the nice thing is that now I can go a little bit up in number density or lower in mass. And so you might notice that at redshift 0, the mass of my centrals is just a little more than Milky Way mass. in terms of stellar mass, which is nice because then again, I'm going to going down in mass to a more representative sample of galaxies. So most galaxies are going to be closer to this mass. And before I show anything about environmental effects, my selection is actually, so I'm gonna quantify this using this very crude separation of quiescent and star-forming galaxies using a rest frame UVJ diagram. And the point is that galaxies that are within the selection box are going to be treated as quenched quiescent galaxies, non-star forming, and everything outside of the selection box is going to be treated as star forming galaxies. Okay, and then I'm going to do again a very simple background subtraction. So now I'm looking at all the galaxies, all the satellite galaxies within some given aperture, and the size of this aperture is determined by the estimated virial radius of those centrals at that redshift. And I'm just counting again. So if this is my central primary galaxy, there are a few satellite candidates, and then to account for background and foreground contamination, I'm going to do the same thing in random apertures. And so now I can go and do this for 100 or 1,000 galaxies in each redshift bin, depending on how many galaxies I get in that bin. And so what I'm getting is this. So there are a few things here. First of all, this is the fraction of non-star forming galaxies as a function of look-back time or redshift. And so these are galaxies within the selection box, within the quiescent selection box. There are a few things. First of all galaxies get quenched with time. So if given enough time, everything is going to be quenched. That's the first thing. Second thing is that if you look at just the background, so these are the random apertures, galaxies in the random apertures, you get, again, this gradual quenching. If you look at the primaries or the centrals, you get, again, the centrals get quenched more rapidly than the background, which is fine, which is what we expected. And you can explain it using, for example, the Beerenboim and Deckel and Beerenboim halo quenching, for example. At this point, I have much more to say about the centrals. So if you're interested, please do come talk to me. But the interesting thing here is that if you now look at if you focus on the blue points, these are the satellite galaxies. So the quenching of satellite galaxies is actually affected by the halo in which they live. And you see that there's a gradual quenching of the satellite galaxies, and it's significantly higher at any given redshift compared to higher than the overall background population of galaxies. And so at redshift 2 or so, the satellites are as quenched as the background. They're not more quenched than the background. But as you get to higher, as you give it more time to evolve, and as you go to lower redshift, the satellite galaxies actually get quenched more than the background population. And so I think this is a really nice, thank you. This is a really nice sign. This is really nice evidence for environmental quenching inside these groups. And remember, these are not massive clusters. These are groups that are going to be similar to the Milky Way, essentially, by redshift 0. OK, so just to summarize, so I showed you so I first showed the radial distribution of galaxies in massive groups. And I showed that there's this remarkable balance between in-halo mergers and accretion into the halo. And the last thing I showed was that star formation in group galaxies, and these are no longer all that massive, is actually affected significantly by the halos in which they reside. Thanks.
Questions and comments? Yes? You.
I had one comment, one question. So you say that most of the galaxies are in groups. Now, if you believe in hierarchical clustering and CDF, that cannot possibly be true. And the answer is actually the two answers. Every galaxy is in a group. If we believe that there is all hierarchical clustering, so there is a all center and always there is a satellite. At the same time, if we cut them at the same Stochastic velocity or rotation velocity, that most of the galaxies are not in groups. Only a small fraction, about 10% will be, meaning subgroups.
So when
It doesn't require comments. But could we have a look at your plot?
thanks.
You can
It all
look at that.
depends on the magnitude limit, right?
What?
It all depends on the magnitude limit for the satellites.
No, if you cut them at the same
Lower
magnitude
the
limit,
magnitude limit and get
if you cut
every
them at the
galaxy-
same magnitude limit, most of them will be distinct halo centers.
Even distinct halo have dwarf galaxies in them.
Then all galaxies will be in groups.
So it's sort of, yeah.
I think, yeah, okay, we can.
So the projected number density of galaxies has a slope, projected slope -1, which means in 3D -2.
That's right.
Which somehow comes along with the GOTO, with the Millennium simulations, which cannot be possibly true because the slope should be -1 in 3D. How it could be -2 in 3D?
That's what we observe, and the slope is really close to -1.
Projected.
Projected, yeah, of course projected. I can only look at projected.
So which means that 3D will be -2.
Exactly, yeah.
Which means that we can, I mean, in the central part of Navarro and Conway, right, this is most we can get will be -1, not -2.
One second, again, this is what comes out of the observations. I mean,
I'm talking about
No, but
simulation.
he's not
This
in
is
the
for
central
galaxies.
part. He's
No,
at
no.
tens of kiloparsecs
It's a
and more.
GOTO, which is the simulations, which is Millennium. How you can get that?
oh, okay.
Anatole is confused about your sizes. You're going out to much larger radii.
And then probably in the -2 part.
No, the
and then-
-2 part, absolutely.
No.
Oh, okay.
So maybe I'm not, okay.
You should
Just
settle
look
this
at the
out.
distances on his plots.
Yeah, no, it goes out to a few megaparsecs.
Yeah, this one.
There you go,
Yeah.
yeah.
And
At
so
100
probably
kbc.
10,
At 100 kbc in a cluster.
That's steep.
In 100 kbc in a cluster, you're in the art of the -2 regime.
that's
But you're not the clusters, it's all galaxies, right? It's not like really clusters.
No. These are galaxies that are within a factor of 10 less bright than the central galaxy. So
So it's dominated by clusters.
These are the satellite galaxy distribution around the centros, so that's a cluster profile.
right,
Yeah,
cluster or group.
yeah.
Mostly groups, yeah.
And
First, I think that this can be explained by tidal stripping, but if you can go back to your second to last photograph.
Yep.
Yeah, this one. It seems that there is a constant delay in the quenching of satellites compared to the centrals,
Right,
of about 2 gigayears.
This is the point that I made last week.
right.
Right. So that's very interesting to explain. Maybe it has to do with the fact that satellites has to go all the way to the center, dynamic friction, all the way to the center of the big halo before the environment of the halo in the inner part affects them and quench them. And maybe this takes 2 gigayears.
Yeah.
There's something to think about.
No, I absolutely agree. I think that there's definitely something to be said about the effect of environment. Absolutely.
It's not
And how they, yep.
constant delay.
Yep.
okay, Sandy.
I have a question about what your study shows about the way galaxies grow in mass.
Mm-hmm.
So I was surprised to see you saying that by virtue of mergers, galaxies could double in mass every 3 or 4 gigayears. I carry around the notion, perhaps flawed, that actually most of the mass comes in as gas, and not as preformed stars. Could you comment?
Yeah, absolutely. No, so I didn't. So I didn't say that galaxies actually grow or doubling mass through mergers. I'm saying that in terms of mass, there's definitely enough mass there that even with just mergers within the how many of them actually end up merging with the central from redshift of 1 to 2 to 0?
Not
It's
all
probably
of them.
not all of them. It's almost likely not all of them.
Yes, but you showed that in several redshift things.
Right.
And it was true even from like 1 to 1.4, so clearly all of them.
No, that only means that whatever merged with the central ended up being replaced by another galaxy into the halo. It doesn't necessarily mean that all of them got merged with the central. It's just that whatever merged got replaced with another galaxy. That's all it is.
Yes, but then we just heard that the quenching is delayed by only 2 gigayears, which sort of implies that there's rather rapid throughput of these satellites through the halos. What you just said seemed to indicate that they would just sort of be moving extremely slowly through the halo.
Yeah. So from what we know, that's not the case. I mean, things don't move slowly in kind of nice circular orbits fall into the center. Actually, most of the galaxies, and this is not what I've done. I mean, most of the galaxies do fall in nearly radial orbits in and out of the galaxy.
No, but orbit decays some way.
Right, we're talking about orbit decay time.
Right. So again, within the galaxies that are within the halo and will end up merging, I mean, on what time scales, I can't say from this.
But let's move on.